So I think we'll get started. So first of all, thank you very much to everyone for joining us this afternoon. My name's Deborah Ives. I'm the Marketing Director for TigerGraph in EMEA. I'd like to welcome you all, wherever you are joining us from in the world, and thank you, as I say, for taking the time to join our session today, which is all about entity resolution with a native parallel graph. So as we get started, I'd just like to go through a little bit of housekeeping. We do have, oops, maybe we jumped ahead a slide there, Richard. We do have, thank you. We do have the opportunity for you to ask questions today, and we really encourage you to enter your questions into the Q&A box that you'll see at the bottom of your screen. You are all muted today, but can still participate with any questions that you might have. And we have allowed time at the end of the session to answer your questions. The webinar will be recorded and will be sent to you along with a copy of the slides probably early tomorrow. So moving on, I'd like to introduce our guru today, and that's Richard Henderson, who is our lead solution engineer based here in the UK. And as you can see, he has extensive experience in data and solution architecture. And so without any further ado, Richard, let me hand over to you for today's session.
Thanks very much, Deb. Hopefully you can hear me okay.
Yes, we can.
Excellent. Okay, so we're talking about entity resolution today, which is quite it's almost the basic use case that happens before you do anything else with graph. We find that almost every single time we start with the idea of how do you get data into the graph and how do you link it together, since the whole point of a graph database is the ability to link together information. So the way we're going to cover it today is I'm going to talk about just what we mean when we talk about entity resolution, which hopefully should be reasonably familiar, but it doesn't hurt to go through it. Also the different methods that are applied when people are doing entity resolution, not only with graph databases, but generally. Then we're going to focus in on what are the steps involved if you want to do entity resolution. And we're finding the same pattern occurs over and over again. It's really not that, not unexpected, although there is a little bit of, some of the detail can get a little bit complicated, but it's worth it. So we'll go through that. But the point here, and it says here, there's two steps. First of all, record matching and linking is the key point of entity resolution. So by matching, what we mean is we need to find two records and that match in some way. And I'll say what I mean by some way when we get to it. And then ultimately, once we've decided that two records match, then we want to link them together. And then step two, once you've got that, what can you do with that? And this will show how it all links into the downstream use cases that are associated once you've got your entity resolution done. After that, I've got a demo for you. It's probably our most recent entity resolution demo, which has a certain machine learning aspect to it, which hopefully should be pertinent for these days, but it shows just the sort of power that you can get by being able to run analytics directly in the database. And then, of course, at the end, we'll do Q&A. So moving on. I guess the idea of this is to show why do you do entity resolution? And this goes back to an old joke about the idea of blindfolded people seeing an elephant, is that when you're looking for a user or whatever entity, when we talk about entities, generally we're talking about either users or user accounts or some other central piece of data or central thing in the world that you have data about. And often the data that you do have about, for example, an account, is very specialized to the particular department that is actually using that data. It could be that a company has had a merger, for example, and they have multiple accounts that they want to consolidate. But the difficulty is that you have different information about each account. And so this cartoon is an idea that just by having lots of very specific views of a user doesn't necessarily give you enough information to give you the holistic viewpoint. And the fact is that without the holistic viewpoint, you don't have the full picture. And so therefore, whatever BI tools or any sort of downstream use cases you have, if they don't have the full picture, then they're unlikely to be as targeted as you'd really want them to be, or indeed they can be completely wrong, as is the case here. So what we're really talking about here is duplication. So if I have one user who has 2 accounts in my systems, then immediately you've got a problem where you don't know whether that should be the case or not. It may be that the 2 pieces of information, say their names differ. Which one is the correct name? You need to decide which one is the correct one. Addresses can be different. There can be very, very many different ways in which, by not having this single viewpoint of the customer, you're essentially stuck in a situation where you can't know what is the correct information which you're going to apply. So immediately you've got a data integrity issue. What you need to do, and this is what entity resolution is to try and join these up. First of all, you've got to identify when they are in fact duplicated, and that's the first problem. But ultimately, once you've decided that they are the same thing, then you want to put them together and hopefully get this holistic viewpoint on the user and say, okay, now I know who the user is. And once you've done that, then you can combine the information, and that gives you this holistic viewpoint that we're just talking about. So just to give an example, and this is a very common one, and we see this quite regularly. And in fact, we'll have some examples later, some use cases which deal with exactly this. When people visit websites, they may not be registered, or if they are registered, they may be registered on different names, different email addresses, different accounts. So this is specifically the case where you have lots of different visitors coming to your website and you really don't know whether they're the same or not. The idea is that ultimately you want to be able to compare the two using whatever attributes you've got available so that you can bring them together. In this particular case, we have examples of names, for example, of putting names into forms. So you have Ken Yang, you have Qikong Yang, and are they different or are they not? Because it's often the case that particularly when people have unusual non-English names, they might use nicknames, or they might use their original name depending on which form they're actually putting it into. So when he's online, his online presence might be Ken Yang, but when he has to write into a more official form or he has to do an application for something, then he will use his correct family name and so forth. The question is, how do you link these together? Because ultimately you need to be able to link them together so you can act appropriately when you're dealing with the person, know what their address is, make sure that your data's got the integrity we talked about. Now we can see here that there are other points as well, is that even when the names are the same, you might have differences in the address. In this particular case, you have Pittsburgh and Pittsburgh. Now, it may be that you think, oh, well, one's obviously a typo of the other. That's not a problem at all. But it turns out that there is a Pittsburgh in Massachusetts, and there is also a Pittsburgh in California, and these are actually both correct. So those names, it's not necessarily a typo. And it may be that, in fact, they are, in fact, different people who just happen to have similar, quite common names. So the way we do it in Graph is very much the case of we use all the information available. So on the previous screen, you can see that, and I'll go back to it, you can see that really we're dealing with nothing but names here. So we can use this gives you some clues that they're likely to be similar, but because you're not using all the information available to you, it means that you're not necessarily able to do this. And so on this subsequent slide, this is jumping straight into a real use case. This actually is something we've got a customer, Zillow, who are one of the largest real estate companies in the world. And they do online real estate where people go to the website and they look at the houses that they might like, and they don't actually have to register. Generally, people will only register at the point where they want to book an appointment, for example. But the problem is that means there's an awful lot of information about what these people are actually preferring, what are they looking at, to try and work out whether you can recommend the appropriate houses to them. So this is a classic recommendation problem where you want to recommend the relevant products to them. And equally, what you don't want to do is annoy them by giving them products they've seen before over and over and over again. So the idea is, what other information do we have that we can use in order to see whether we can actually improve our ability to link these people together? And if we do that, what sort of improvement do we see in business performance? I mean, there's got to be a point to doing this. This is something that is worth bringing out, and we'll see it quite a lot. So when we look at the clues, one of the things we do is, for example, we can look at which houses do they actually look at. People will generally, when they look at houses on a website, they will tend to revisit certain areas of the website if they come in again. We can put cookies on their browser, and we can use cookies for linking. We can use third-party cookies. So if they go to Facebook or they go to Google or any of these other places, then you get additional cookies, additional ways of identifying a person, which are made available to anonymously to people who actually buy that information from Google and Facebook. So the idea is that you have a lot of information that you can use. Further information, what else? We've got device IDs, whether your device looks the same as the other device. You can look at the IP address, where are they coming from? If two people are coming from completely different parts of the world, then chances are they're probably not actually the same person anymore. So that's the question. You go, okay, maybe I don't need to actually do that. So maybe if we can use all of that information, then it gives us a chance to actually improve our ability to link users together. And once we've linked them together, we can use the information about what they've seen in order to give better recommendations. And specifically, in this particular customer, Zillow, what they saw, there was two things they measured it on, which they were really cared about. One was whether the sessions got longer. So if you recommend good houses to people that they want to look at, that's relevant, they will tend to spend longer on the site, actually clicking through the recommendations and making sure that they actually find what they're looking for. And the more houses they look at, the more chance there is that they'll actually want to fix an appointment to actually view a house. The next direct measure is, do they actually book more appointments? Do you actually sell more product? And those are the two red things that they looked at. They've been a long-term customer hours, and they see 10 to 20% uplift in both of those dimensions when they do this kind of thing. The next one to look at is healthcare records. So the reason healthcare records are interesting is that they are incredibly diverse data sets, very low quality data sets often. But when you are a company who is offering healthcare, as they do in the States, but not just in the States, over here as well, in Europe, then customer journey, customer experience, the penalties associated with getting things wrong in this space are severe. So therefore they thought, well, we need a much better way of doing things. So it talks here about providing the right care to the patients. The point being that if you combine the wrong person's medical records together, then their treatment may be incorrect or their history may be incorrect. And so that's pretty significant. The other point is that when customer journey, when people are ringing up because they want to talk about something that's happened, it could be something that's happened in the distant past on a different system from a different provider. Therefore, merging the records so that you actually have this full history makes a huge difference to the approach which can be taken to whatever their healthcare journey is, which is going to be provided. What they did was they took all of the data from these diverse systems, they linked them together, they used graph to do it, and again, they were seeing this number of 10 to 20% comes up a lot. 10 to 20% improvement in journey, and that represents billions of dollars potentially, and also in terms of avoiding being sued for getting it wrong, but also in terms of improving cost, and also in terms of the cost to support somebody, and also improves their opinion of you. It tells them, customers generally, if they find that their interactions, they're not having to repeat the same information over and over again, then that improves they feel happier about dealing with somebody. They feel that the provider is actually caring about them to this extent that they at least get the information right about you. And here we go. This is ultimately what they were finding, that they had a huge improvement. This is with a company called Amgen. Ultimately, we've got another top three providers in the States who are actually using us. pretty much for exactly this thing. And the first step of all of this, of the customer journey activities that they were doing and the recommendation that they were doing, the first step was entity resolution. Final example here is to do with government services. The key for this was the question of whether the right people were getting the right benefits at the right time. And the difficulty they had was that there were 10 to 15 different government departments, all having different registrations of users, all providing different benefits. The data was not very well linked together. And so as a result, they didn't know who was not getting benefits that should and who was getting benefits who shouldn't. So it's a real simple problem. Fraud avoidance. You want to make sure that people are claiming, not over-claiming. They're not trying to claim the same thing from multiple addresses, for example. Equally, you want to make sure that you're providing the appropriate benefits. This was talked about the benefit white space, the idea of discovering what if in a household, okay, are we actually giving them everything they need? Because there are certain household benefits available. So for example, if somebody is a carer for somebody who is disabled, then there are carer benefits that go with the disability benefits that could go together within a household. So the idea was to be able to identify those and suggest them. And then finally, we come back to the easy thing, which is how much does it cost to support users? Generally, particularly in social settings, the cost of support is very high because the casework is quite difficult. It involves an awful lot of personal contact. It's not like the online world where you just wait for people to click a button. So as a result, any improvements there make a huge difference. And now, from having actually done this work with Graph, which is able to actually combine this information, then it's allowed them to greatly improve their ability to detect fraud in the first place. So, and also to improve their reputation. So it's gone from being a government department that was widely disliked by the people who had to interact with it to one where they're now seen as what they are, which is a tremendous service to the community. So how does this work? A good thing to think about is there's two major ways in which this all goes together. You have deterministic and you have probabilistic ways of doing things. And then I've added in machine learning at the bottom because that's quite interesting as well. It actually influences particularly the probabilistic side of things. So the deterministic one is really the easy one. It's the one that everybody does right now. So one of the things I haven't really talked about is what extra do you get by using a graph database, particularly using TigerGraph, a graph analytic database, than you do, which you could probably do with just your normal relational databases. Well, the deterministic stuff is the one that anybody can do. When there is a specific field, whether it's an ID field or it's a piece of information like a particular piece of information, such as here we have the social security number, for example, or a national insurance number or whatever is available, then it's really easy to match them up because basically it's an equals sign, and running things to see whether things equal each other is something that we've been able to do for many, many years. And that's pretty much what you expect. The difficulty with deterministic is that occasionally people make mistakes. And when that happens, you have to fall back into the next method, which is here, which is the probabilistic side. And at that point, you have to decide how similar are things? Are they the same name or slightly different name? When I say different, how different are they? What is their similarity score? If somebody has entered an ID number, it could be, as we talked about earlier, if they've entered that incorrectly or it's been typed in incorrectly, how do you know that they're the same or different? It all starts getting a little bit trickier. And when there's significant differences, then just using a single piece of information, as we saw much earlier with Kenny Yang, is maybe they are actually different people. So the problem you can have is you can have this false positive problem where you falsely link people together. And what do you do about that after the fact? Particularly, what do you do about, first of all, tracing that you've actually done, that happened and why it happened? And then how do you fix it after the fact? All of these things are things that are very difficult to do with standard ways of doing entity resolution. in terms of machine learning, the key, this comes back to having got a probabilistic way of doing it. How do you improve that probabilistic side of things? Because now when you're fuzzy, you've got to draw a line somewhere between what is definitely the same, what might be the same, what is definitely different, what might be different. So finding where the correct boundary is there is something that is where machine learning excels. And that's exactly what you're looking for. Is you want to be able to layer machine learning on top of it so that you can incrementally improve your performance as time goes by, as you learn more about the space that you're working in. I would say that on the previous one, there was one missing point, which I think is worth having. I'll go back there so not to distract. The manual entity resolution method. Now, it may seem really obvious, but let's say we find two things that might be the same or might be different. What do you do about that? And the key is you need to be able to support the ordinary human beings in their job to actually do that, to actually make it work for them. And the way you can do that is by making sure that when you present information about what the machine thinks about the world at that point, what do you do about it? And the thing you do about it is that you have to support their work as well. The idea is that your automated matching system should not live in a little black box of its own, such that when you get these situations where you're not sure whether it's right or not, you don't want to be in a position where they have to start again from scratch to work out what's gone on. If you can provide them the reasoning, you make it explainable, you make it interpretable, then that allows you to actually to enhance their ability to do their job. And they can look at it and go, okay, so the machine saw the same name, saw the two Pittsburghs, thought they were probably the same person because of that. But I happen to know that those are in fact different places in different parts of the country. And I can see from the times they were logging in. So humans can add their own wisdom, their own experience into this, and they can then apply that to it. And then of course, you have your machine learning system. Overnight, he can see these manual decisions have been made and go, so how could I have worked that out for myself? How could I have reduced the amount of records that I've given to somebody to get going? So here's an example of deterministic entity resolution. And this is the old way of doing it. And you can see that what's happened is that we've got two customers. We have a certain amount of information associated with that. And we've decided that for whatever reason, in this particular case, let me see, what have we decided makes them the same? We've decided that we're going to merge those values. And so we literally merge the information between user one and user two by basically pushing them together. Now, that's all very well, but you can see that's kind of a one-way process. We've lost an awful lot of information about how those people should be mapped together. But nevertheless, this is something that's very easy to do. And this is pretty much what people normally do, is they effectively push together the information. They rely on exception processes to deal with it after the fact, but those exception processes are done out of band with the way that the entity resolution is done. In a probabilistic situation, you get a bunch of entities, so a bunch of users. And what you're attempting to do is to use some sort of scoring system to decide how those people are similar based on information. So we have pink lines here, which are probably going to other information like names, schoolwork, and activities associated here. And the idea is that we can use the level of similarity between two people's additional information in order to come up with a score. And what we do here is we add edges. So here we're getting into a very graph databasey type thing when we talk about edges a lot. An edge is just a link, but links are independent entities in a graph database. And when I say independent, what I mean is that adding a link after the fact between A and C or B and D is something that we can do at any time. You don't have to factor that into the schema. You don't have to worry about changing the schema to add new links. So immediately you've got a new capability, which is useful. What we also do, particularly in our flavor of graph, is we can actually put a number on here to say what the score is. And we can actually put more information than that. We can say why we thought it was this score. We can say which method worked. We can say under Rule 36, because the two, they went to the same school at the same time, they're more likely to be the same person. And so this now gives you a bit of an audit trail. It gives you that information I talked about earlier about assisting humans to actually do their job after the fact so that you can deal with it. And also you've got effectively a trace of how that linkage occurred and why that linkage occurred. So you've brought back in band the idea of how do you deal with exceptions, how do you deal with audit, compliance, and all those other things that might actually be important if you've made the wrong decision, or indeed if you made the right decision. The other thing, of course, is that information can also feed into your machine learning. It allows it to tune your scores, tune all those parameters that say just how important is it that they went to the same school at the same time. Probably quite important. How important was it that they lived in the same town? Maybe less important, because that's a very large area, and so it's less likely to make a big difference. But if they lived in completely different towns at the same time, then the chances are they are not the same. And so you can create this fairly complex set of rules and really apply it in the way that you want to. What happens is, once you've done that linkage, you basically remove the links that are lower than a certain score and you keep the links that are higher than a certain score. And that allows you to see, okay, so A, B, C, and D, they are now, we'll assume they're the same person, and E, F, and G, they're the same person, but they are different. Even though they might sound slightly similar names, one of the classic things to do is to use Soundex to decide whether things are the same. But in this particular case, given the rules that we've got, we can say, okay, they're definitely different people. So this brings us back to the 2 steps of solving entity resolution. And the first step here, record matching and linkage. And from the examples we've given, you can see that it's pretty much what you'd expect it to be. Matching involves scoring the closeness of 2 particular pieces, 2 users in our examples. And we do that using rules, using deterministic sides, using whatever systems we've got. Then once we've done that, then we need to link those records together, which is we change or add to the data structure in a way that is actually going to tell us that we believe there is a linkage. And as I've said, the idea is then that you, with a graph, that you can actually add information to the existing database, and that allows you, it avoids the situation where you're doing something one time and you can't go backwards and you have no trace of it. So that's very useful. The other is that the rule-based approaches and things like that, you can run them directly in the database like a query. In TigerGraph particularly, we have a full-scale graph analytic language, which is going through the standards process as we speak. And that allows you to do things extremely rapidly. We talked about some of the previous ones. I'll talk about some of the big numbers associated with this as to other reasons why people have used us. And the other point is that once you've got that, you can actually get extra value. As we say, if you have more information about a user because you've combined information that's available, that allows you to make better recommendations, better scoring, better assessments of whether they're actually there or not. And even the way that they are linked is now useful information for making these assessments. And we've talked about machine learning. There's machine learning downstream as well. One of the things I often say is that graphs are a tremendous way of enhancing the features which you expose to machine learning downstream. And so what we're seeing is a lot of people are relying on graph to give this contextual information, and in this case, the entity resolved contextual information, this enhanced data set forward, and that means that their machine learning has more information to work with, and so they get better results. So just kind of a review of what we talked about. 2 records can be linked when they have similar user profiles. So this is information that would be directly on their record. And that's something you think, well, okay, I can probably do that. It's difficult to do at scale, but I can probably do that with my existing data systems. But then we start talking about, what about if we're logging in from similar IP addresses, when there's a list of IP addresses? What about if there's a bunch of devices, a bunch of phone numbers? What about cookies? There might be hundreds of cookies. In a cell tower, just how many cell towers did we go through, did you walk through with your mobile? Then at that point, the amount of contextual information starts getting very high, and running this towards your standard analytics system starts to get a bit expensive. It starts to become a little bit difficult. Once you have similar home and work addresses, once you start adding more and more information, once you start adding things like timescale co-occurrences, then the amount of information that you get, the multiples can be anything 100 to 1,000 times the information that you had if you were just dealing with the name. And that, of course, improves your ability to resolve the entities very quickly, but it also means that it starts becoming a little bit difficult to deal with that volume of data and to be able to analyze it in a timely fashion using record-driven databases. So that's NoSQL databases. They're mostly record-driven or purely event-driven if you're in the Cassandra world, or if you're using a normal relational database. And relational databases are designed to store hierarchical documents, really, whereas this is actually a network of information. And so if you've got a network of information, you probably want a database that deals in networks, which is really what we're talking about as a graph database. And that intuitively suggests why graph databases are very successful in this space. So what does that mean? It means you take the records you've got. That can be batch records, or it can be event records, so individual events like transactions, payment transactions, phone calls, pings for devices, all of those things. You're going to put them into the graph, and in the graph you'll generally have the records you care about, so the users we talked about, and then you have all of the attributes which are associated with the records that you have. The idea is that you take that information, and you've already got a reasonable amount of connectivity, because you'll notice that there is a, just here, if you can, I don't know whether you can see my mouse, but we've got two green records here, two users, and they have a common attribute between them. So immediately, as soon as you put the records in the database, you're starting to see the linkage happening. And it's exactly that weakly connected linkage that we see is what we do, is to try and strengthen that to ultimately go via the matching algorithm to the linked entity network that you can see on the right. What sort of matching algorithms do we have? Ones we generally use, cosine similarity is very, very common. And really, all that means is that you're effectively counting the number of common items, or the level of common items that there are between two of the entities. And you're using a way of normalizing that to give you a number between 0 and 1 to decide how similar they are. And it's really as simple as that. It's using a very simple approach. And the reason that's good is because simple is efficient, and efficient is fast. And that's where we want to be, is we want to be able to deal in very large amounts of data. It also works very well in the real-time context, in that if we add links later, then we can recalculate the cosine similarity, and it still works. The other one is rule-based, of course, and we've talked about those as well, which is when you're saying what things you care about and how much you care. And we've already mentioned that. So if you have the same first name as someone, probably not so much indication that you're the same person. If you have the same last name, maybe slightly more of an indication. If you have both the first name and the last name and the home address, then suddenly you're in a very good situation. It's very likely that you are in fact the same person. There's 3 different ways of linking we talked about, but it's worth discussing. Matching links. So the matching link is when we just add edges between the data. So we just add edges between the green guys saying, I think this guy is the same as that guy, and we've already seen that. The new one we're adding here is this idea of a unified entity. And this is actually our favorite, because it gives you, it separates the before linkage world and the after linkage world very clearly. Here we've added this idea of a unified entity. Sometimes this can be called the golden record as well, as another way of describing this when you're dealing in master data management entity resolution. So you create this golden entity, but the source entities, you'll notice in the graph database, they don't go anywhere. All you're doing is exactly linking together the information without changing that information. And that has 2 very useful properties. One is that you can, your original information is still in the same form, and so it's very easy to inspect at this point. And this comes back to our idea of how do we assist humans in their work, because we know that we're never going to get 100% fix. Then the other point is that if we want to change the linkage, then that's something that's easy to do because we haven't thrown anything away. Everything is still exactly as it was when we imported it. All we've done is add these extra links to suggest how these are linked together. And the third one is back to the traditional idea of taking all these records and putting them together. Now, we can definitely do that. That's easy. But the difficulty with that is at that point, you are in fact throwing away information. There is a fourth way of doing it that we haven't talked about is we can hybridize these, we can bring them together, particularly the matching link and the unified entity vertex. You can do both of those things at the same time. When we do the demo, we'll actually show something like that. And that kind of gives you the best of both worlds. And matching links are very fast because you can go straight from user to user to user. So because they're directly linked, but you also have this unified entity. So you still have this ability to understand what you did and when you did it, and effectively aggregate the data into a golden record if you want to. Once you've got all this, you want to do your BI on linked entities. And the results, as I say, generally 10 to 20% is a very conservative figure on the improvement, because of course these improvements compound. Also, the risk reduction, particularly when you're dealing with compliance, is huge, and the cost of dealing with that, of when things go wrong, can be extreme. They may be rare, but they can be very high. And the idea is to, therefore, any reduction, even a 10% reduction there, is going to have a multiplied reduction further downstream. So we have more accurate delivery of data because your data is effectively being cleaned, because you've been able to, the merging process, it reduces noise, it removes noise, and at least highlights as well where there is any difficulties, say, for example, if addresses have changed. So addresses is really important. People do move house all the time. Finding out what is the most current address is actually quite a key fact. And so if you can work out that the address you've got in an account is incorrect, then that might possibly be the reason why they haven't paid their bills, is because they haven't received them. Being able to find those sorts of information is very useful. Recommendation results with a higher converting rate we've talked about. That is a significant improvement. One of our largest customers is Wish.com, the largest by volume retail platform in the world. And they see a tremendous advantage in being able to merge user behaviors as they come on, so they can very rapidly learn what they like and suggest better products to them. Finally, in Customer 360, this comes back to the cost of actually managing users. And if you have a good 360 view of your customer, then at that point, when you support them, you know everything there is to know about the person. So therefore, you can basically provide them a better service. And better service in this particular instance is also less expensive. And so you've got this, again, you've got this compounding of benefit which comes to people. And it's exactly why people do this. If you want to get slightly technical about it, when we do this BI, then what we talk about is weakly connected components. So you started off with your users knowing a little bit about the different elements of users, just like the elephant at the beginning. Once we've linked them together, then now we have actually improved our information about the whole. So by solving this weakly connected component problem, we've effectively improved our position as far as the data is concerned. And that's why all downstream processes are effectively enhanced by this. So a couple of quick examples before we go to demo. These are real customers. One is Marketing Cloud. So they get cookies from everywhere. And what they do is they need to link them together into a single person. And that allows them to effectively provide their clients with information that they can use in order to offer the correct products, which is what marketing is all about. They were already doing this, but the problem they had was that they just couldn't do it fast enough. And so by moving to our product, given 1.7 terabytes of raw event data per day, that's a lot of data because these are really small pieces of information. By using us, they found that their data load time actually moved down to minutes when they were running it continuously, and they could run it multiple times per day. And so therefore that was no longer a blocking factor on their ability to expand their business. Creating the initial unified device vertex, in this case for households, it was happening in minutes rather than in an overnight batch. And that allowed them to do much more interesting things during the overnight period, particularly running their machine learning, running their complex BI reports, and running multiple iterations of that overnight. And that allowed them to get into a space they wanted to get to, where they wanted to get into the machine learning space particularly. But they found that it was taking so long to prepare the data in the first place, they weren't being able to do it. Finally, they were able to offer a new service, and that new service was the ability to do household segmentation in real time, and that allowed them to actually start doing the recommendations directly. So rather than just providing demographic information to their clients, they can now actually give them very specific recommendation information, recommendation attributes, so that they can just get their business going. Example TV2 is TV network. This is quite a common one. We have two enormous customers for this in the media streaming area. The problem they had was that they essentially sold and resold their product through a lot of different channels. They sold it through cable, so direct to users, to customers. That was easy. You know exactly where that's going. But they also had what's called OTT, where they were effectively selling it over streaming and over mobile channels as well. And then they're also selling it through third parties as well, where they were syndicating programs out through the syndicates. And that they completely lost control at that point of who the person was. They just didn't know. The difficulty they had, what they wanted to do was find a universal identifier that they could use to attach to a user, really to find out who was watching what. The difficulties they had was, initially they were running it with a bunch of Spark jobs. Apache Spark is very well known, extremely powerful, and very scalable analytics system. But the difficulty is that when you're dealing with an awful lot of data, and that data is streaming in continuously, then those Spark jobs were taking longer and longer and longer. And so as a result, they were getting less and less value from it. Also, it was starting to cost a lot of money because they were needing an awful lot of boxes just to deal with the fact they were moving so much data around. The logic they were using to define who was which user was effectively quite rigid and quite complicated. They'd end up with an awful lot of rules. But, you know, and that made it quite difficult. But the thing that was really hurting them was that because they didn't have any sort of audit trail of the decisions that were being made by this definition logic, it meant that they really didn't know whether it was high quality or not. They had no idea. They weren't getting enough information to be able to get that using machine learning or whatever to get some sort of virtuous loop where they could assess their performance, so therefore improve the situation. What they did was they used us. We improved in every dimension here. So instead of going from batch jobs, we went to a fully streaming real-time solution. The user definition logic was changed to be much more like the graph-based approach, which we've shown, which was much more flexible, much easier to change the logic as they went. And again, because the original data was still there, because we didn't actually manipulate that data, all we did was decorate it with the decision logic on top, it meant that they effectively had an audit trail and that allowed them to improve their situation. Flight company, this is the problem of, again, people buy tickets from anywhere and all they've got is a name. This is particularly for internal flights, so they didn't necessarily have things like an ID, like a passport ID, that would allow them to actually see who had done what. And so as a result, it was quite difficult for them to actually market to those people. So instead they used TigerGraph. They reduced their latency on turnaround on this, and they're originally running on mainframe, SQL Server, and Oracle, and a bunch of others. We reduced the latency of that by reducing the complexity down to a few minutes in order to handle mini batch updates. So basically per flight, they could then do a quick entity resolution to work out whether a person had actually flown with them before, whether they had preferred seating arrangements, whether they had preferred food they preferred to eat. So if and that basically made them a much better service to the customer as a result. Their BI queries were actually ended up being streaming BI queries. So they had a dashboard rather than having to press a button and run a report once a day. That meant that they could be very, very reactive. And we're back to this point when things are fast, then you can do really cool things with your machine learning. Right, demo. So this one actually is the streaming device demo. The thing here is we have a bunch of information. Just to give an idea, this is actually, you can actually get this demo directly on TG Cloud. TGCloud.io is our, you can go in there, you can actually run production on there if you want to, but it also has a free tier, which allows you to actually experiment, and we have solution kits, and this is the entity resolution machine learning solution kit. First of all, we start with a schema, and I won't go through all of this, but what I would like to point out is that we're starting with a bunch of account information, and that account information has emails, IP addresses, phones, devices, addresses. So this is the sort of information that they have associated with a particular registration. The difficulty they have is they don't know whether these are the same users or not. So the idea is, can we consolidate the account information so that we actually have the full set of information for any particular user? This is running on a very small box. In order to make it run quickly, we've got around about, I don't know, there's just under 500,000 objects in the database, which is around about 90,000, no, 80, oh, you can see the numbers here, 83,000 vertices and 270,000 edges. This is quite a small amount of data. From our point of view, this is a very small amount of data. This loads extremely quickly. This one, I think it peaks at around about, I think it loads the entire 272,000 row set in less than a second. It's not unusual to be inserting over 1 million objects per second, even on a very small box. We have people who are doing 100 times that, who are pushing terabytes of data through our systems in real time, because it's scalable, because you can load in parallel. If we look at the graph itself, just to show, we haven't got, there's no users in here. Just make sure I'm not cheating. Keep myself honest. Now, we'll go through the process, and I'll do it in much the same way as you would if you went through the solution kit. So the first thing you want to do is we're going to run user initialization. What user initialization does is it effectively associates a single user, in this case 900, for a single user per account. So every account is now associated with a, if I double click, you can see we have a user here, a new user 335 associated with an account 335. And we can see there's another user 591, 591, and so forth. So you get the idea. So this is just a one-to-one insertion, which is, you know, pretty easy. The next thing we do is start when it starts getting interesting, and this is the linking. So if we look at user linking, what we do is we establish a set of weights that say how important is each of these pieces of information to deciding whether it's the same user or not. And so we've got IP address, email, phone, last name, address, device, and so forth. And the other is we've got a threshold that says how definite are we that it's definitely one user, and so therefore we'll definitely link these together. Generally, your threshold will be slightly lower than 1.0. We're just, for the sake of argument, we've set it to 1.0 here. The idea is that it will compare every user with every other user. Now, if you were doing this in a standard database, that would be an n-squared problem. So if you had 1,000 users, that would be 1 million comparisons and so forth. In a graph database, it does not have to be that way. It works in a much more linear way. And so that means that we can run this very, very quickly. So if we run it, okay, it's linked 1,800 users together. Let's see if we can actually see some of those users. So I happen to know that 407 is an interesting user. 707, I think, is the other one. I think, and these two, let's see if they've linked together or not. Yes, so we can see that they have lots of common information. So the question is now is, how do we actually make these, get these to actually link together? So we've done this. What we need to do is we actually need to group the users. And so by grouping the users, this is the point where it says, okay, I can see these are the same users, so now I'm going to actually link them together. So I press that. Okay, it's groups users into 600 separate users now. Converged false here says that because it's done a grouping, it may be that we need to do another iteration of this. But if we come back to our two users, which were not directly linked before, but they obviously had quite a lot of things in common. Let's see, are we going to find it? Yes. Now we can see that actually we've collected them. Now we have a single user ID, which is ID 107, which is now connecting these three users together, 407, 107, and 707. And so as a result, you have exactly what we're looking for, which is a single user, which is attaching to multiple accounts. And this actually, we set it up so that it effectively aggregates all those pieces of information together into a single set of information. If we come back to our queries that are runner, now we've done the grouping, we'd need to do the linking again, run the linking. It's linked to 0 users. And so because that means it's effectively finished, yes, we can see it's finished. So we have effectively linked together all of the information. And just to give an idea of what that means downstream, we can look at, for example, tell me something about a particular input account. So in our case, I think it was account 107. Now, from account 107, we can see all of the information associated with that user. I'll just make it a bit bigger. And we can change the way that it's laid out. And you can see that now we have this commonality of information, whereas before it was separated and distinct. Now we can see all of the information associated with this information, which is quite interesting. If we come back to the queries, just one more query, and then the main thing we want to know is, okay, so what video will they want to watch next, for example? So I've got 107 as our guy, top 5, and we can actually run the recommendation directly in the database. So using all the information, all the films that they've ever watched, all of the video plays that they've seen, then we can get a top 5 result. And ultimately the top right 5 result you see here is that the film that they're most likely to want to watch next is called Death Trap, as it happens. And the score is put against each of those so that you can actually run it. And we do real-time recommendation on this basis. So it starts from entity resolution and it moves all the way to the business value. And that is everything I had on the demo side. So any questions?
Thank you, Richard. Yes, actually, we do have some questions, and we've got about 5 minutes or so left. So we'll get through as many as we can. Any that we don't get through, we can follow up individually. But first question, can entity resolution be done online, for example, for real-time update?
Yes, specifically because we're not modifying the initial information. It means that whenever you add a new piece of information, then that piece of information can be directly integrated, and we can fix up only the things that are relevant to it. So that means that you can, in a very scalable way, do incremental update. In fact, we recommend doing it that way. That's the best way of approaching it.
Okay, thank you very much. Oh, the questions are coming in thick and fast here. How did you decide the weighting on each attribute used in matching algorithm?
For the demo, we did it purely we just put in some fairly random numbers, the ones that seem to work well. In the real world, what you'd do is you'd do either a statistical analysis of your history, or you'd run some machine learning over it to work out which one was most successful at doing it. So that's the easiest way. But also, you can interpret any rules you've already got. You can start from there. You can start from your rules and you can interpret that directly as the weights. It makes it quite easy.
Okay, and another one. How do you typically visualize, present these results back to clients?
For things like recommendations, stuff like that, then it's that top 5. You would get a standard report. For investigation teams, they will often want to click through. So they want to be able to click through the data. So they might actually look at, the stick and ball model that we showed. That can sometimes work really well for forensics teams in particular. Love that. But we do present a REST API, so you should be able to, whatever you've already got, you can probably still use with what we're presenting as well. We're not here to change. We just want to enhance your world. We don't want to completely change it. So the idea is evolution rather than revolution. So you'll definitely be in a position so you can use it the way you want to.
Okay, probably one quick last one. The graph database is a unique format. How is it compatible with other databases such as Cassandra?
You can get away with it. Now, and when I say that, it's not, I'm not saying, I don't want to say, oh, it's really easy, you just press a button, it works. We do offer a direct importer from JDBC, for example, from relational databases directly into our database. The one thing we do is we provide a very easy way of mapping the edges, which is the key problem, the links. And that's really easily done. So it's not difficult. It requires a certain amount of manual intervention because you're correct, it is a different structure. But having said that, it's usually pretty quick to do. It's not difficult. Any data architect takes about a day for them to work out what it means, how the mapping works, and then they can usually do it very quickly. And as I say, this automatic import facility, which we're pushing out soon, really illustrates the fact that it's not necessarily a particularly difficult thing to do.
Great, thank you, Richard. And there's just a couple of minutes left to go before we hit the top of the hour. Maybe we could just go through final bits of information to give you regarding upcoming events and some additional resources. As I mentioned, we will be sending out a copy of the slides and also a copy of the recording of the entire webinar to you. But just so that we'd like to draw your attention to an upcoming event that we have on the 29th of July, which is all about accelerating data science with Python and TigerGraph. And you can see the link there if you would like more information or would like to register, or any of your colleagues. And finally, here are some links to some additional resources. Richard mentioned some of them already, but you can take a look at our cloud solution kits. You can download Developer Edition. You have access to a developer portal or join our community. And if you really would like more information, you can join a weekly demo that we do every Friday at 10 a.m. That's Pacific time. So it just remains for us to thank you very much for your time today. Hope you found it interesting. There's Richard's email address. I'm sure he would be happy to answer any questions
Yes.
that you might have. And thank you again for your time, and wish you a very enjoyable rest of your day or evening or morning, wherever you are. Thank you.
Yeah, thank you very much. I'll speak to you soon, hopefully.